Hello everyone, I am Srimanti and I am currently working as an ML engineer. So I'll be discussing the derivation and maths behind classification, which is another top ML algorithm. I have covered log likelihood before in this video, and I would say it's kind of a prerequisite for this video. If you already know about that, then without any further ado, let's start. So the first thing that comes is, what is the problem that we are trying to tackle here? So basically the first question always is, what's the data set? What does the data set look like? So it looks something like this. As I said, we'll start with the simplest form first. So x1, x2, and y. So y is basically either 0 or 1. We'll be tackling binary classification first. So y is either 0 or 1. Let's say it looks something like this. And x1 could be 1, 2, 3, 4 maybe. And x2 could be anything. 0.5, 0.9, 1.0, 1.1, anything. So these x1, x2 are the two features. And y is our target variable, which is either 0 or 1. And we want to predict y given x1 and x2. So now comes the graph. Exactly what are we trying to find here? So we'll try to plot x1, x2 here, x1 and x2, and then we'll try to get the points here. So let's just say these are the 4 points that we have. So now what we're trying to find is this line, because this line would be distinguishing these points. Suppose this point has y equal to 1, and this point has y equal 1, this point has y equal 0, this point has y equal 0. So this is the line that we're trying to find that differentiates the y equal 1 from y equal 0. Because suppose now we have any kind of point, suppose x1 is here something, and we have given x1 and x2 and we find it here, then we know that this point lies on this side of the line, so y will be 1. It's as simple as that. I hope you get this. So basically x1 and x2, given x1 and x2, what is our y? That is our target to find. Given x1 and x2, we want to find y. Fun fact. So logistic regression is also called classification. Do you know why? Drop your thoughts in the comments. Okay, coming back to this one. So this line in classification is called decision boundary, which is very important. Remember this term. So what is the definition of this line? This line is the maximum distance from all of the points. So what do I mean by that? So here actually we are tackling the distance between the points. So these differences, this is the di. For each point x1i and x2i, we have this point which is di, and this di we want to maximize, because we want the line such that it differentiates the two 1 and 0 completely. Okay. So what is exactly the equation that we're trying to solve here? So yi given xi parameterized by theta. This is the equation that we're trying to find. Why are we trying to find that? Because if you remember correctly, this is log of this summation I equal 1 to m being the total number of data points. M being the total number of data points. So this equation is the log likelihood. So this is very important. So that is why we are trying to find this and we are trying to define this term. So this is actually yi given xi parameterized by theta. This is actually the Bernoulli distribution. Because either the probability, we are trying to kind of find the probability of it being 1 or 0. And Bernoulli means only two values we can predict, 1 or 0. So that is why this is like similar to the Bernoulli distribution. Now that we have got this out of the way, we know what we are trying to find. So now comes the di. Let's focus on di. Let's get an equation for finding out di and formalizing that. So if you remember, I just now said these are all di. So this line, this side is a positive side of the line and this side is the negative side of the line. So we can either decide So we can either decide, we can decide the direction. So let's just say this side of the line is positive and this side of the line is negative. And then this di, let's denote z as di. So now this is very important to understand. So listen carefully. So this di, it can range from positive infinity to minus infinity. So we are trying to find a function. So di can range from positive infinity to negative infinity. Okay, so now if di is 0, let's say for a point, the point is lying on the line. So we don't know whether it's positive or negative, whether it's 1 or 0. Let's just say positive 1 gets classified as 1, negative gets classified as 0. So if the point is on the line, we don't know whether it's positive or negative. We don't know whether it's 1 or 0. So the probability is half. So di equals 0 should have the probability as half. We are now trying to find the constraints for finding the function that will fit di perfectly. So di is 0, p is equal to half. What if di is positive infinity? Which means that probability will be 1. And then di, suppose it's negative infinity, then probability will be 0 of getting classified as 1. So we are finding that we are now currently thinking of p as the probability of getting classified as 1, this one. So if it's on the line, then it's 0, then probability is half. If it's infinity, which means we know for sure that it's 1. Point is 1, so p is equal to 1. And if it's negative infinity, we know for sure that the point can never be 1, so its p is 0. So now, what function fits all these conditions? Yes, so that is the sigmoid function. Write this down. This is the sigmoid function. So what does this look like? So now we are going to see how the sigmoid function looks like. We denote it generally as g as a function of z. It would be 1 upon 1 plus e to the power minus z. This is a sigmoid function. So let's put in the values and see if it satisfies it or not, that we just now saw. So if z equals 0, then what is gz? It is half. Perfect. If z is infinity, what is gz? Gz is 1. Perfect. Because 1 by 1 plus e to the power minus infinity, this would tend to 0, so we have 1. And if z is minus infinity, then gz is equal to 0. Why? Because 1 by 1 plus e to the power infinity, this tends to infinity, so 1 by infinity is 0. So now we have a function which satisfies all these points. So now we have our ideal function. So sigmoid function is what we are going to use here. Before I delete this, let's see the curve of the sigmoid function. So this is 1, this is 0, this is half. So at half we have at 0, z equal to 0. So this is z, this is gz. So when z equal to 0, then we have half. When z equal to infinity, we have 1. And when z equal to minus infinity, we have 0. So somewhat like this. This is the sigmoid curve. Remember, this is very important, comes in interviews, comes in placements, wherever, jobs, internships. This is extremely important. College exams, gate exams, whatever. So this is very important. So now we have the sigmoid function out of our way. Great, one down. So now we'll find out the log likelihood. So probability of yi equal to 1 given xi parameterized by theta. Probability of yi equal 1 given xi parameterized by theta. Earlier it was probability of yi given xi parameterized by theta because yi was continuous. In distinct case, it's a little bit different. So we'll take yi equal 1 and we'll take yi equals 0 and we'll get the formula for these two. Then we'll see what to do, how to combine them together. That's very interesting as well. We'll come to that. So this is the yi equal 1 given xi parameterized by theta. So we know, we just now found this 1 plus e to the power minus. So now what is this term? What is this term? So basically, if you remember, when I was talking about the decision boundary, in binary classification is going to be a straight line. Obviously, because we are trying to divide these points, this distance we are trying to maximize. This distance we are trying to maximize from all the points. So this is a straight line. So now we know what is the function, which is the equation of a straight line. It's y equal to mx plus c. But this is only when it has only one feature, which is x. So we have here two features. So then what are we going to do? So this is going to be y equal to theta 1 x1 plus theta 2 x2 plus theta 0. So we have x1 and x2 as I showed earlier in our data set. And so we will use this equation. So basically, what does this equation mean? And how can we write this equation? So I'll just play a short video here where I've talked about how we can get this equation and write it in the form of y equals theta transpose x. So here it starts. It's just a few seconds video. So yeah, so you'll understand why we are writing y equals theta transpose x from this equation. Now there's an interesting way to write this. So we want to write it in the form of a vector so that we have simple equations to solve instead of this complicated equation with all the variables. So now, okay, so now theta. How do we represent theta? So theta would be n plus 1, right? Total number of thetas will be n plus 1. Those theta 0 to theta n for each of these x1 to xn feature. So theta matrix would be theta 0, theta 1 till theta n. 1 n plus 1 cross 1. This is our theta matrix. And our x matrix looks like this. I already said m cross n. Right? M being the number of data points and n being the number of features. So now our y would be m cross 1. So now if you can see carefully, so theta 0 has 1. This is very important. Try to understand this. This is the trick that you will use in most of the algorithms when you are trying to find the any solve using the vector formula. So this is the one that we have. So let's say if we had x0, it would have been 1. So what we'll do is we'll add a column here of 1s. So then we'll make this. Let's make this. So this would be, these are the n features we have. Now we'll have another column of 1s. So this becomes plus 1. So this becomes n plus 1. So now you can see this is m cross 1, this is m cross n plus 1, this is n plus 1 cross 1. So we have a matrix multiplication here. So if we have theta transpose, what would theta transpose be like? 1 cross n plus 1. And then we'll have x. So we can write x in the form of like n plus 1 cross m as well. So that just depends on how you express x. Let's do that. Suppose we want to write x in the form of n plus 1 cross m. N plus 1 cross m. So this is our final x coordinates. So this would be n plus 1 cross m. Now here 1 cross m, which is our y. So we can say y transpose, or we can represent it in the same way as x. So in that case, y would be 1 cross m. So it doesn't really matter when you're trying to solve. This is just the way we choose to express this formula, and we choose to relate y and x and theta. So this would be 1 cross m. So now you have this 1 cross m. So you have this equation, which is like very common, y equals theta transpose x. So now that we know this, we know that here we are going to have, since this is the probability yi given xi parameterized by theta, so this is going to be theta transpose xi. Because yi is 1 that we are focusing right now. That is why this is the positive distance. Yeah, so this is the positive distance that we are using, 1 plus e to the power minus theta transpose xi. Why are we doing that? So basically what we have done is, if you remember di, we have written that as theta transpose xi. We don't want to get in this perpendicular thing, so we are just going to take theta transpose xi, and then which is kind of like removing all the constants yi. So yi equal 1 given xi parameterized by theta is 1 by 1 plus e to the power minus theta transpose xi, which is our distance, positive distance. Great. Now the next thing is, you can already guess what this is going to look like. 1 by 1 plus e to the power minus of minus theta transpose xi. So basically this is g of minus theta transpose xi. And this was g of theta transpose xi. Remember g, which is the sigmoid function, minus. So this is going to be 1 by 1 plus e to the power theta transpose xi. Great. So now we have this out of the way. It's very important to get the intuition for this, because once you understand this, 90% of the problem is done. So yeah, so we are 90% done. So now comes the gradient descent function, and how we are going to use this log likelihood function that we just now found out in order to find out the parameters, that is theta 1 and theta 2, that is theta basically, how we are going to use that. So we'll be using gradient descent, obviously. That is the only way here. So now we need to formalize that. So basically maximizing log likelihood is same as minimizing the loss function. So I hope you've seen the video where I've explained why this is the case. And I'll reiterate it. If you do not know this, then it's important to know this before you proceed. Okay, so I'm going to assume that you know this. So basically maximizing the log likelihood is the same as minimizing the loss function. So now we are going to write a function for the log likelihood. So what we had earlier was likelihood and of two distinct cases. Now we want to combine them together. So this combination, trying to understand this, is very, very, very important. I cannot stress it enough. Okay, so I'm going to use the formula directly here. It's not much. The previous page where I was discussing, it was the likelihood function. And now this is the log likelihood, just using a log. This is the function. Summation I equal 1 to m log of probability of yi given xi parameterized by theta. Great. So now we are going to break this down such that we can accommodate two cases. Listen very carefully. So this is the first one. So when y equal to 1, we want to take the case when y equal to 1 here. So basically our data set is divided into points such that y equal 1 and some have y equal 0 with some points x1 and x2. So we want to find out those points which have y equal 1 and take them here in the first part of the function. So how are we going to indicate that? We are going to use something called an indicator variable. So I is basically, so let me just go into this a little in detail. So basically, what is an indicator variable? So suppose you have a list of functions. Suppose you have y here. So 1, 1, 1, 0, 0. Let's say this is our y data set. And we're using the indicator variable. So if we do here 1 of yi equal 1, this means that whether y is equal to 1 or not. So this is true. So this will take the value 1. Here also it will take the value 1. Here also it will take the value of 1. Now here, is yi equal to 1? No. So this will take the value 0 and this will take the value 0. So do it with me. So if yi equal to 1, function I equal 1 to, there are 5 points. So then the answer would be what? 1 plus 1 plus 1 plus 0 plus 0, which is going to be 3. So this is the basic funda of indicator variable. So now that we know indicator variable, we can move on to the next part of this function. So what is going to look like? Now you can guess it. I think you can guess it. yi equal to 0 given xi parameterized by theta. This would be indicator variable of yi equal to 0. Great. So whenever yi is 1, we are going to use this because probability of yi being 1 parameterized by theta given xi. And whenever yi is 0, we are going to use this. So now this log likelihood can be expressed like this very easily. Now the work is almost done. I can say it's 95% done. So now what we want to do is just put in this value. We know this value. So let me just clean this up. Okay, so now what we're going to do is do the substitution and then differentiate that and equate it to 0, right? Now we know this one. Probability of yi equal to 1 given xi parameterized by theta 1 by 1 plus e to the power minus theta transpose xi. I just now wrote it. And the other one is probability of yi equals 0 given xi parameterized by theta is 1 by 1 plus e to the power theta transpose xi. Okay, so now what we're going to do is substitute. So this function would look something like this. This would be yi by yi itself, because you saw that when I was showing that graph. So if yi is 1, then this will be 1, right? And if yi is 0, this will be 0. So we can just take yi and then put in the function here 1 by 1 plus power minus theta transpose xi. And for this one, we know what is going to be. You can guess it. 1 minus yi. So if yi is 1, this will be 0, which is what we want. If yi is 0, this will be 1, which is exactly what we want. Perfect. So now we have 1 minus yi log of 1 by 1 plus e to the power theta transpose xi. Now we have this. Great. So now, as soon as we have this, our work is done. So it's now 100% done. So we just need to differentiate this and equate it to 0. And then we'll have an equation for our thetas. And we can just use that. We can use it like in gradient descent, as you know. So I'll just come to that. So first, let's simplify this before we differentiate. This minus is because I'm putting it here. And this would be, this would have a minus already. So we can just yi minus 1 log of 1 plus theta transpose. Cool. Yeah. So now let's remember this formula. Now that we have this formula, then let's differentiate that. Delta of LL theta equal to 0. I'm using delta again because we have multiple dimensions. Okay, so now we'll differentiate this one and equate it to 0. So let's differentiate. We have this equation. This is basically our LL theta at this moment, and we now want to differentiate this. So let's do that. So summation I equal 1 to m minus yi. We're differentiating with respect to theta. So this would get differentiated. So as we know, differentiation of log x. Differentiation, what is differentiation of log x? It's 1 upon x, right? So ddx of log x is 1 by x. So that is what we're trying to use here. And one more thing we're trying to use is ddx of some f of x. Then it is going to be df dx upon x. This is going to go down, and then this will be df upon dx. So let's use that. So we put this down, and now we're going to differentiate this with respect to theta. Yeah, so with respect to theta, what would that look like? This would be 0, and this would be e to the power minus theta transpose xi, and this would be minus xi. Correct? Yeah, got it. So this one done. Now the next one. So what would this look like? Let's see. So yi minus 1 would be in that way. Keep that. Oh, it's the same thing. So the below it will go e to the power theta transpose xi, and here it will be theta transpose xi multiplied with xi. So this is the way it goes, and then we're differentiating this one. So e to the power x differentiation is e to the power x. If you know, ddx of e to the power x is e to the power x that we're trying to use here. So e to the power x differentiation would be this, and then differentiating this with respect to theta would be xi. Great. So we now have got both of this out of the way. This would get plus because of 2 minuses. Now, yeah. So now if you see, so this term and this term is similar. So we're going to club them together. Now, we are going to use a trick. Listen very carefully. Otherwise, you will miss it. Listen very carefully. I'm going to use a very simple trick, very old trick in the dictionary, but I'm going to use that. So if you see here, we have, what do we have? E to the power minus x, 1 plus e to the power minus x, right? So now, let's do that. So if I convert this 1 by e to the power x upon 1 plus 1 by e to the power x. Now get this up here. We would have 1 by e to the power minus x. We're multiplying with e to the power minus x. We are multiplying by e to the power x. So we would have e to the power x plus 1, correct? These two are same. You agree? So now we are going to use the same thing with e to the power x. So e to the power x we have 1 plus e to the power x. So now we are going to do is 1 by e to the power minus x upon 1 by e to the power minus x plus 1. So now What will this be? Let's multiply by e to the power minus x. We would have 1 by 1 plus e to the power minus x. So does this look familiar? So now if we convert this one like this, we have the same denominator and we can combine these terms. Excellent, right? Remember this trick. This will come in handy later as well. Great. So now you just saw what I did. So I'm going to use that. I'm going to convert this one into this form. You will soon realize why I'm doing this one and not the opposite. yi e to the power minus theta transpose xi 1 plus e to the power minus theta transpose xi multiplied with xi. And this one, I equal 1 to m yi minus 1. Let's do this one. So what is this going to look like? 1 by 1 plus e to the power minus theta transpose xi. Correct? You got it? This is extremely a very neat trick that we use, and it solves most of the problems as you just saw. So now we have the same denominator. We can combine these two terms. So yeah, so let's do that. So let's simplify. So what do we have here? Let's see. We have 1 by 1 plus e to the power theta transpose xi, and here we have yi xi. From here, e to the power minus theta transpose xi. We have plus yi xi from here, and we have minus xi. So as you can see here, if you just take yi xi common, we have 1 plus e to the power minus theta transpose xi. Yes, we are very, very close to the formula that we want, the simplified form. So let's do that. yi xi, let's take that common. And we have 1 plus e to the power minus theta transpose xi upon 1 plus e to the power minus theta transpose xi. So these two get cancelled. And this is minus xi upon 1 plus e to the power minus theta transpose xi. We are nearing the term that we're trying to find. So do not forget this though. It's very important. This derivation is extremely important. It's gold, pure gold. So great. Now that we have this, so we are trying to find out. Yeah. We are almost. We are like literally at the end. So I'll just take this one out, put it here. So this is going to be, let's take xi out. So we are going to have yi minus 1 by 1 plus e to the power minus theta transpose xi multiplied with xi. So does this look same? Does this look familiar? This is what? This is the sigmoid function. Correct. So let's put that in here. yi minus g of theta transpose xi multiplied by xi summation I equal 1 to n. Perfect. This is the formula that we were looking for. Now that we have this, we know what delta theta, LL theta looks like, and we will just now use our gradient descent formula. So remember this formula, we have spent a lot of time and a lot of effort and hard work to get here. So this is very, very, very important. And if you've got this, then you practically understood classification. You have got it. Yeah. Perfect. Now let's do that. So now we are going to do the gradient descent. So if you know what is gradient descent, so basically gradient descent means, I'll just repeat it like in short. I have told about it. I've spoken about it in my earlier videos, but I'll just tell about it in short. So this is where we are starting. So this is our loss or our log likelihood that we are starting. Okay, so if we're not talking about log likelihood, then this would not be the curve in that case, because in log likelihood, we're trying to maximize it. In loss function, we're trying to minimize it. So the curve would look something like this. So here we are currently, this is our log likelihood, and we're trying to reach this point, which is our target, which is our maximum log likelihood function. So if you have this, so this is the target that we're trying to achieve. So what are we going to do? Simple. So we are going to use our gradient descent formula. Theta t plus 1. So we'll initialize theta with some random values or 0. And then we'll follow this curve. Yeah. So we're going to follow this curve. So theta t plus 1 is going to be theta t minus eta delta theta LL theta. sorry, minus of this. So practically it's plus. Why is this? Now said we are going not in the direction of the slope, we are going to maximize the likelihood. That is why we need to move in this direction, which is very important. So now this is our gradient descent formula. So I'll just write it out again. If this is not very clear, plus theta, delta theta, delta theta. What you just need to do is just place the function that we just now derived in here, and you have it. And you can follow it for as many epochs as you want until you get convergence. This is the learning rate. And learning rate determines the rate of convergence. And we have theta at the end of this. Perfect. We've literally come this far, then you deserve a medal. You are a genius. You've understood everything and you can tackle any problem of classification now, be it in interview, in placement, in job, in GATE exam, in college exam, anything. Great, great, amazing. So now just a simple thing. So basically now that we have theta, we know that the equation of the line is going to be theta transpose x. If you remember that I was using earlier, theta transpose x, correct? So now it's very important to find out. So now we want to find out the equation of the line, right? So just remember one thing that we did. So when I was saying that our di is theta transpose xi, right? So, and g of di or g of theta transpose xi would be half if di is 0. Remember this, right? So let's get that from here. So 1 by 1 plus e to the power minus di is theta transpose xi. So I'm going to put this in here equal to half. Now solving the equation, what we have, theta transpose e to the power minus theta transpose xi, 1 plus is equal to 2. So this would be 1. So now theta transpose xi is equal to 0, which is exactly the equation of the line that we're looking for. And this will be the decision boundary. Remember this one that I was saying earlier. This is the decision boundary. The equation of this is theta transpose xi equal to 0. Perfect. Now we have got everything. Now given xi, we can easily find out where the line lies. And based on the line, we have the probability and we know on which side of the line it lies. If it's a positive one, then y equal to 1. The classified point is 1. And if it's on the negative side, it's going to be 0. Great. Amazing. Now we are done. Now you can tackle any problem related to classification. And yeah, I hope this answered all your doubts about this topic. And if you have any questions, please drop them in the comments. I'll try to answer them. And yeah, please stay tuned for new videos. Thank you.